All right, Ken, we'll get started.
Okay.
All right. Thank you, everyone, for joining. Ken, can you just move to the first slide, please? All right, great. So today we are going to hear from Ken Lanier, and he's going to discuss the challenges of high-power processor and ASIC testing. So I'm going to pass it over to Ken.
Very good. Thank you, Kaylee. So welcome to what will be a short but hopefully useful discussion of testing high-power processors and ASICs. And when we talk about high power, we are mostly concerned in this case with testing what happens on the power pins themselves. So if we look at large digital devices, I can tell you what you probably already know. Power supplies for these devices are getting larger. The VDD is going down, as you can kind of see in this bottom plot that talks about sort of over time what has happened with both VDD voltages around 0.6 volts and external voltages, IO voltages, which are slightly higher. And again, at test, we have a bigger problem than anybody else who's using this device, because when we test the device, we run structural scan tests, which by definition are flipping lots of transistors at once and causing really the worst case power supply draw that device will ever see. So if you look at what's in a processor tester, there's really only two types of instruments in it. The first is digital instruments. Now, when we talk about digital instruments, we think about complex instruments that run patterns, do timing, capture all our failures, and do lots and lots of other things. And then the other one is sort of the power supply. And the power supply has a seemingly easy job, which is basically to go from 0 to some voltage and back again. But as it turns out, as we go through these test programs, the power supply is the more important of the two, for the simple reason that it primarily determines the quality of the device and the eventual yield from test based on how well it performs. And there's a couple aspects to that, and we'll talk about both of them. The first is sort of what happens statically. Now, when they sell processors, there's usually some balance between the VDD and either the frequency the device will run at, the number of cores that will run, things like that. So when these devices are sold, you usually try to find a sweet spot where the device will do enough work to be useful, and it will be at a point in the VDD curve where it's not drawing inordinate amounts of power. So if you're in a mobile device, for example, this VDD actually changes over time and adapts to what the processor has to do. And if you're testing it and you want to make sure it works at some given VDD voltage, well, it's pretty straightforward. You want to set the power supply to some VDD voltage and see if it works in an ideal world. Now, no tester is perfect. Every power supply on a tester, every instrument on a tester has some error associated with it. So if your power supply in the tester is off by a little bit, there's two things you can do. First, you can set the power supply a little bit higher. And when you do that, you're going to get really good yield, because if the power supply is at its minimum level, the device will still pass. Now, the other thing you can do is you can actually set the power supply to the nominal voltage and expect that it's actually going to end up being at a lower voltage, potentially on some testers. If you do that, then you can sell the device and say, hey, it works at the nominal voltage. But as it turns out, if you get a tester where the power supply error is large, you may start losing yield. So you really can't win. In the first case, I have to sell the part and say the VDD has to be higher. And if I'm setting power supply to a higher level, what happens is that the device will get hotter during the test, and oftentimes we'll have to slow down patterns. And in the second case, the people you work for won't be happy, because if you do get tester power supply error that makes the voltage lower, you will, as I said, eventually get some yield impacts, which are very, very expensive for these devices, because the biggest part of the cost of the device is the silicon itself. So the theme here is pretty simple. It's millivolts matter in this case. So if you look at any tester spec, the thing that we care about at Teradyne, if we look at a power supply spec, it's always voltage force accuracy is one of the key things that we would try and differentiate on. Now, I said there's a static problem, static accuracy. Well, there's a second problem, is that the power supplies are not static. They tend to move around. And that's because the amount of power the device draws will simply vary based on what it's doing. So if you were to start a scan pattern, pretty simply what happens is if you start flipping all these transistors at once, the power supply, the IDD is going to have a certain inrush, and the resultant VDD will go down slightly. So this inrush, depending on the device, it can be hundreds of amps. And if the power supply droops enough, even if it's momentary, the device can fail. And so now you're back to the same problem of, well, gee, my tester might have too low, my device might see too low a power supply, in which case I could have failures I didn't intend and my yield is lower. So it's really the same problem we were talking about in the last slide. But the problem here is it's more severe. It tends to be a bigger droop, and it's less predictable because it's entirely dependent on the pattern content, exactly how many relays are flipping, how many transistors are flipping at any given time. So it's very difficult to predict what the impact of this is going to be. If you want to find out how big an issue you have, typically what we do is we look at shmoo plots, and everyone probably understands what a shmoo plot is, but typically what happens is you just record pass-fail results as you vary parameters, and the ones that are very popular to vary are VDD and the scan rate, the scan shift rate. So the pattern rate effectively. And so you can expect that as the VDD goes down and the test frequency goes up, you'll eventually get failures and you'll get passes in the opposite condition. And then there's sort of this area in the middle where sometimes it'll pass, sometimes it'll fail. So it tends to be a little unstable. And what we really want to do is the lower we can, the farther out we can get this sort of failing region, farther we can get it down into the right, the better. So, I have an example from a device that we did recently, and now this is a little bit reversed. The axes are going in the other direction, but you get the idea. There is a test condition where we have a certain VDD we programmed at a period of the test program, and we tried it on one tester and got a result that looks like the thing on the left. We tried it on a second tester, got a result that looks like the thing on the right. And clearly, if you looked at this, you'd rather have the one on the left because, I could potentially go down and spec my part either at a higher frequency or a lower voltage, knowing that I have a test capability that will consistently validate that. So what these plots look like is a huge deal because in the end, it determines how you can spec your device in terms of battery life, overall power draw, how fast it works, how many cores you can turn on at once. All these things will actually come out of these plots if you really want to go validate all these specs while you're testing it. So the other thing, when we talk about testers, the question we get is, how much power can you put in your tester? Well, I think almost anyone can put an infinite amount of power in your tester. You could fill up every single slot in the tester with a power supply, and you could have thousands and thousands of amps. But saying you can put in a lot of power supplies really doesn't mean anything at this point. It's not the question you should be asking is not what's the static current you can support, but how big a current step can you support? So if you had 4 devices in this case, and they had a total of 600 amps of power supply, and there are devices that really do this. If you wanted to test these things 4 at a time, well, across the tester, what you need to support is a lot of current. In this case, in the worst case, I suppose, 2,400 amps. So the tester would have to support a step on all the power supplies collectively of 0 to 2,400 amps. And it would have to stay in spec, which means that voltage group would have to be, whatever it was spec to be by the vendor. So again, if you're looking at testers and you want to ask of how much power can you do, again, the question you want to ask is how big a current step can you do and still have the tester remain in spec. The other thing that's interesting about these power supplies is we called them DC supplies in the beginning. We said, well, it goes from 0, goes to VDD, but as we're discussing, a lot happens between 0 and VDD. If you have a voltage group in this case, so this is the case where the pattern has not started, the pattern starts, and then the power supply, this is the VDD voltage, will eventually recover. And this thing in the middle, that's an AC signal, right? It's a step response, has lots of broad frequency content to it. And what you're trying to do is you're trying to get that step to be as low as possible and the recovery to be as quick as possible. So take your step function and basically put storage, energy storage on the DIB to be able to provide a momentary sort of burst of energy to the device when it needs it. So when we look at designing DIBs or DUT boards or probe cards, whatever you want to call them, we look at the spectrum and we look at, well, what are we going to do in each band of the spectrum? Because we need to, this is a broadband signal and we need to make it look as good as we can. So again, what's the spectrum of your power supply output? Kind of a funny question, but it's actually really important. So this can be easy or it can be hard. Traditionally, if you have a certain power supply and you need to compensate for its performance, you wind up putting some sort of big bulk capacitance on the DIB to handle the low frequency effects. To do the mid-band stuff, you do more caps on the DIB or something that's not right at the device, but again, is reasonably close. And then for the high frequency stuff, you end up putting yet more caps, either as close as you can get them. So in many cases, those capacitors are in the device package itself or on the probe hardware. So again, this is where the performance of the AC performance of the tester power supply matters a lot. Because if you have a really good power supply, in this case, really good, means it's fast and it's very accurate. If you do that, you get to eliminate bulk capacitance, and you can generally limit yourself to one type of capacitor on the DIB to handle the remaining needs. If you have to put multiple types of capacitors in the path, the problem, of course, is that you get you get different resonance frequencies. If you were to look at the response of each particular capacitor type, and if you get these resonances lining up for different capacitor types, really, really bad things happen. So, the better the power supply in the DIB, to a first order, it allows you to go down to one type of capacitor, eliminate the bulk capacitor. It gives you good settling times. So I said there's one type of capacitor. And then the other thing too is that, if you have huge amounts of energy storage on the DIB and these bulk capacitors, and you touch down on a device and there's a short and for some reason the capacitors are still charged, that's a lot of energy that can be going through probe needles. So the biggest complaint that we hear from customers is that these probe cards are really expensive. I mean, people spend more on probe cards than they do on testers, believe it or not. And if you start burning up probe needles, that can add up to a lot of money every year. So again, if you can keep the overall capacitance value as low as possible, it reduces one of the things that could potentially cause probe card damage. We've talked about all this. Well, if you start the scan pattern, you get this huge inrush, and we've talked about, well, how do you solve that problem? And we've talked about, well, you want a good power supply, you want to have good bypassing, and so on and so on and so on. Well, the old joke is, doctor, it hurts when I do that. Well, and the doctor says, well, don't do that, right? So, if this huge current inrush is the issue, then what do we do to get rid of the huge current inrush? And there's a great paper that was published a long time ago now by a couple gentlemen at AMD, which I found really fascinating. I talked to customers about a lot, And they said, well, fine, if the current inrush is a function of the scan clock rate, well, why don't you start with a slower scan clock and then speed up the scan clock after n number of clock cycles? And, the number of times you do this, it will allow you to sort of take this one big voltage dip and turn it into a series of smaller voltage dips. So that's one advantage, right, is that you get to, not have as big a droop. The other advantage is that when you get into this faster part of the pattern, you can actually run this part of the pattern faster than if you were running it all at sort of the same rate from start to finish. So in this paper, what these gentlemen demonstrated was overall test time improvement of up to 10 to 15% by being able to do this. And and it's simply because the bulk of the pattern can be run at a higher speed than it would be in the case where you had to run the pattern all at one rate. So this is kind of a cool idea. What you need to do that is pretty straightforward. You basically just need the ability to change tester period or frequency on a cycle by cycle basis. So in the case of the Teradyne testers, you do that with something we call time sets. What time sets allow you to do is basically change the period rate, from one vector to the next. And the key requirements here are pretty simple. You need to be able to do that seamlessly. There can't be any dead cycles in between. It can't be like, change the frequency and wait kind of thing. And you don't want to have special microcode, things like that, to have to do it, because all these patterns are automatically generated. So it's not like you can put, these settling loops and things into every single cycle, every single pattern, if you're generating tens of thousands of them. But if you can keep it simple, that the pattern construct is fairly straightforward, then it is something you could put back in an ATPG system, so that when you generate your tens of thousands of patterns, they can all have this capability, if you like. So this is, not a lot of people take advantage of this. Some do. Some actually bake it into their scan patterns. You can do it by pattern manipulation if you're upstream enough. But this is kind of a cool way to try and lessen this problem. So the last thing I want to talk about in the time we have is sort of, where's all that power go? The other work that we're doing, we put all this work into putting power into the device. We're also doing a lot of work with our customers and partners to actually, we have to get the power out again. And most of that power is dissipated as heat. And so to a first order, you need to be able to cool the device. That's pretty straightforward. I want to be able to take heat out. There's active cooling. You could get a liquid cooled setup to have a cold plate come down on the device and remove the heat. But what you want to do is you don't just want to randomly cool it. You really want to keep the die temperature as stable as possible, because you'd like the test conditions to be repeatable at a specific die temperature, so that from tester to tester, or run to run, or from pattern to pattern, the test conditions remain as stable as possible as far as temperatures are concerned. And there's a few ways to do that. And we've kind of done work evaluating all three of them. So they kind of come in chronological order, if you will. So the first thing you could do is you could monitor the power going into the device. So if you had a signal coming out of the tester that was signals coming out that were proportional to both the VDD and the IDD, an external power automatic temperature control unit they can multiply two numbers together and get a power, and monitor when the power goes up, and they can increase the cooling. And the cool part of that is that this current increase is the thing that happens first in time. So you kind of get a jump, because these systems have a response time to them. And you kind of get a jump on things if you're monitoring the power supply current. The only downside to this is that the current going into the device does not exactly predict the die temperature. It's a good indicator, but it's not exact. The second thing you can do is actually monitor the die temperature. Pretty soon after the current goes up, the die warms up. That's a pretty quick effect. The problem is that if you go to any fab, whether the die temperature is monitored and how it's reported is all a function of who's designed the devices. So sometimes it's an analog output that needs to be buffered. Sometimes it's a digital output that needs to be read back. And sometimes there's no output at all, especially at package test. So there's a lot of inconsistency with how this is, how the die temperature is reported, how the tester can look at it, and what it needs to do with it. And so there is a pretty significant lag if we have to do a bunch of digital readbacks from the device, make a decision, and send information to the handler. There's a lot more lag time to it than if we just, in real time send over a couple of analog signals. The last thing you can do is monitor the package temperature. This happens last, right? This is a real lagging indicator, and the die's already good and warm by the time the package warms up. So the only real advantage of this is that you don't need the tester to do it. The handler or ATC system can do it all by itself, because all it has to do in that cold plate is monitor the temperature of the device. But the problem, if you see a temperature rise at that point, it's kind of too late to do anything about it. So we've looked at all three of these. We tend to like the DUT power monitor, because our tester happens to support it natively. But again, it's always available. We don't have to worry about the capability of the device. We don't have to worry about specifically which ATC system we're talking to. And as I said, it is a leading indicator. So we tend to have a lot more luck with this DUT power monitor than with the other two. So we've done a lot, as I said, we've done a lot of work on this, and it seems to work pretty well. And that's what I had prepared for today. So I don't know exactly how I did on time, but Kaylee, if there's any questions, I'd be happy to answer them.
Sure. I'm just taking a look right now, and I don't see any questions that came in.
Okay.
But I will say, Ken, can you just give everyone your email address? If they have any questions, they can shoot you an email.
Yeah, I'd be happy to do that. So the email address is very simple. It's ken.lanier at Teradyne.com. You can also contact me through LinkedIn, obviously. The other thing I'll make a pitch for is I do co-chair the Heterogeneous Integration Roadmap Test Committee. And if you want to Google that and see what that means, that would be great. But basically, it's a collaborative effort by different equipment vendors and IC manufacturers to come up with a roadmap for test requirements in sort of a pre-competitive way. And it's tied into the IEEE Heterogeneous Integration Roadmap Group, which is a packaging roadmap organization. So if anybody's interested in helping with that or getting involved or just seeing what we do, you can contact me about that as well.
Awesome. Thank you, everyone, for joining. We'll see you next time.